on the clock. Okay, fantastic. So, welcome to the lecture number, I think, is number 8, right? So previously we had a bit of questions regarding to the orthogonality of Bessel functions and the completeness relationship. Which is going back to the 2 lectures ago. Now we are following the spherical harmonics expansions. So, and what we understand that is if you solve the Laplacian in the spherical coordinate, then we understand that using the separation of variables, then we understand that the phi of r, theta, and phi essentially is given by 2 summations. One is on index L and the other one is on index M, which M is changing from -L to L and L is changing from 0 to infinity. Then for the radial part, we did have a Lm of r power of L plus Blm r power of L plus 1. And then we had spherical harmonics, which was Ylm of theta and phi. Do you agree? Right. And Ylm was the answer to the solid angle Laplacian. So people usually they call Laplacian with respect to theta and of course I mean phi, but I have to be careful. Let's call it the Laplacian with respect to omega. So, and indeed that Laplacian of Ylm of theta and phi plus L times L plus 1 divided by r squared Ylm of theta and phi was equal to 0. Do you remember? I think it was some expression like that, if I'm not mistaken. Let me check it out. Spherical harmonics. Differential equation. Okay. Yes, that was the Laplacian that we had. Fantastic. So, we drive all of the expressions, and what we got also that Ylm essentially are given by an expression which I will write it down. I don't memorize them. I have to look at my notes. Yeah, I have the table now. So Ylm is given by square root of 2L plus 1 divided by 4 pi. Then we had square root of L minus M factorial divided by L plus M factorial. Then we had 2 set of complete bases, one for the theta and one for the phi. So it was PLM of cosine of theta, and then we had e power of I m phi. So that was the azimuthal angle, and that was the theta. Okay, so that was the conclusion that we came with, and it was that Ylm in the spherical coordinates, if we neglect R, they are complete bases. So any functions can be expanded in terms of them. And that's really, really important. Okay. And remember that based on, again, the same discussion that we had, when you define L, which is an integer quantity, is a positive integer quantity, M is bounded from -L to L. So essentially, M will take one of the 2 plus L values. Okay, so that's an important fact that you have to remember. Okay, so when you define L, M also will be defined. When L is equal to 0, M will take only 0 value. When L is equal to 1, M will take -1, 0, or 1. When M is L equal to 2, then your M will take -2, -1, 0, 1, or 2 value. So it's bounded. And I'm sure that you have seen that in the angular momentum space and angular momentum along Z direction. So if you look at the eigenvalues of angular momentum, that will show up in the calculation. So it's L2 essentially, and then that is the eigenvalue of Lz, which is one of them is L times L plus 1. The other one is M in units of h bar, of course. Good. So YLM, they were complete basis. What does it mean? That any functions can be expanded in terms of them. And also they are orthonormal, which means that integral of d omega YLM of theta and phi YLM prime of theta and phi, one of them of course should have a conjugate, then that is given by delta of LL prime, delta of M prime. That is orthonormality. Relation. Okay. And the completeness relationship comes from the fact that if you take the summation of YLM of theta prime and phi prime, YLM of theta and phi, summation is from for any L which is changing from 0 to infinity, and any M which is changing from -L to plus L, that will be given by delta of phi minus phi prime, and delta of cosine of theta minus cosine of theta prime. Okay, so that's the relationship, which is the completeness relation. Okay. So indeed, if you have an arbitrary function of theta and phi, then this arbitrary function of theta and phi can be expanded in terms of spherical harmonics, because it's only two, and we know that we are talking about theta and phi means that the theta phi of spherical coordinates. So that can be expanded in terms of L and M. Remember, M is changing from -L to L. I don't write it always, so I will just write it as summation of these two, and can be expanded in terms of YLM of theta and phi. And that coefficient is given by ALM. Exactly look like Fourier expansions. So this is exactly the same way, but you are doing the expansion in terms of spherical harmonic, which is Legendre, associated Legendre polynomial, and also harmonics. Okay, so how do you find ALM? You multiply both sides by YLM star of theta and phi with different L and M values. So you use the orthonormality relationship, then ALM can be found in terms of integral of d omega YLM star of theta and phi, then G of theta and phi. Okay. And remember, what was d omega?
4 phi.
Was d phi? D cosine of theta. Okay.
Mm.
If you write it in terms of d phi and d cosine of theta, remember the interval essentially for phi will be 0 to 2 pi. For d cosine of theta will be -1 to +1. Okay, because when theta is equal to 0, then cosine of 0 will be 1. When theta is equal to pi, then the cosine of pi will be equal to -1. So the interval is changing from -1 to +1. If you decide to expand this in terms of sine of theta, d phi d theta, then the interval will be from 0 to 2 pi and 0 to 1 pi. Okay, remember that that relationship is important. Okay. There are a lot of important features that you can look at it in terms of these series expansion in terms of harmonics. So let's look at one of them, which is very, very important. They call it addition theorem. The proof is given in your book, and I will just write it down and I will tell you what I mean by that. Assuming that you have two vectors in space, which one of the vector is x prime, the other vector is x. Okay. What is the angle between these two? Let's call it gamma. You can expand this in terms of Cartesian coordinate, which is x, y, and z. And you will find out that x prime, for example, is given in terms of spherical coordinates. That will be r prime. Along z will be r prime cosine of theta. Along theta prime, along x direction will be r prime sine of theta prime cosine of phi, and r prime sine of theta prime sine of phi. This is the vector in the Cartesian coordinate, but expanded in terms of spherical coordinate parameters. All right. So what is going on with x? Oops, sorry. What's going on with x? Exactly in the same fashion, you can write them down in terms of r sine of theta, cosine of phi, r of sine of theta, sine of phi, and r cosine of theta. Okay. Now I'm asking you, what is the relationship or what is the angle of gamma, which is the angle between the two vector of x and x prime? If you take x dot x prime divided by the value of x and x prime, then you will get the angle, which is cosine of gamma. Okay? Do you agree on that? We have done these previously. And cosine of gamma, indeed, is given by, if you do the dot product divided by r minus r prime, it will be sine of theta prime cosine of phi prime. I'm doing the dot product between the upper side. Sine of theta cosine of phi plus sine of theta prime sine of phi prime sine of theta sine of phi plus cosine of theta cosine of theta prime. Okay, you can factor out sine of theta prime from these two, and then what you will get sine of theta prime sine of theta. Then the first one will be cosine of phi minus phi prime, or vice versa, it doesn't matter, plus cosine of theta prime cosine of theta. So indeed, the angle between the two vectors of x and x prime, if you want to expand them in terms of in the spherical coordinates, one it's spherical coordinate, one also can do it in cylindrical coordinate, and then that will be a completely different question. But if you do the expansions, what you will see that from this expression, that cosine of gamma, which is given in terms of sine of theta prime, sine of theta, cosine of phi minus phi prime, plus cosine of theta prime, cosine of theta, this is essentially nothing more than a function of theta and phi, right? Assuming that theta prime and phi prime, they are just parameters for the expansion. Okay, so did you get the point? So this is a function of theta phi, theta prime, phi prime. But for us, theta prime and phi prime, they are parameters depending on the coordinate that you choose. For example, you can do the transformation, you do a rotation, and you can keep the x prime to be exactly along z direction. If you move the x prime to be along the move the coordinate to be such a way that x prime is along z direction, then gamma is essentially that theta angle that you are looking for, okay? So for us, theta prime and phi prime, they are just parameters. So indeed, this expression is a function of theta and phi. What are the complete bases in spherical harmony, in spherical coordinates? They are spherical harmonics. So one can think of expanding the cosine of gamma in terms of YLM of theta and phi, okay? Which will be summation over L, summation over M as well, okay? And what will be the coefficient? ALM of theta prime and phi prime, okay? You can do that and you will get the relationship that you are looking for. Essentially, that will be a bond on which value you are looking for. All right? The addition theorem goes beyond this and says that if you have any Legendre polynomial, Legendre, not associated Legendre, Legendre polynomial of cosine of gamma, then these also can be expanded in terms of YLM of theta and phi. Okay? And what are the coefficients of expansions? These coefficients of expansion only, well, of course, will be function of theta prime and phi prime, as we discussed above. But that will be only given by the spherical harmonics. Let me look at my notes. Let's see where I am. Yeah, it's given by YLM, and the summation is not on L because the Li is identical. The summation will be only on M, which is changing from minus L to plus L. And then with the coefficient, which this coefficient is 4 pi divided by 2L plus 1. This is an important relationship, which we call it addition theorem. Okay? Legendre polynomial of cosine of gamma, the same gamma that we discussed previously, which is the angle between the x and x prime, can be expanded in terms of spherical harmonics. What are the coefficients for these expansions? Is given in terms of YLM, theta prime, and phi prime. All right? The proof has been given in your book. It's not difficult to understand. It's a little bit, just a little bit tricky. I will leave it to you. Usually myself, I will do the proof based on applying the rotation to the coordinates. So I will do it based on the moving the frame, which I don't give it to you right now. Okay. So that's an important point, which you have to really be aware of that people, they use these expansions. I mean, they use spherical harmonics because they form complete bases. And when they form complete bases, then you can do expansions in that base. And we know what are they, okay? So let me give you an example. Is there any question, by the way?
Actually, I wanted to know why one of them doesn't have like L prime, M prime.
M prime?
L prime and M prime. That Y star, theta prime, phi prime. Why the indexes for both of them are L and M? Why one of them doesn't have M prime?
Look at the expansion. So if you remember, that is PL of cosine of gamma, right? What was the gamma? If we discuss, we say the cosine of gamma is a function of theta, phi, theta prime, and phi prime. All right? And we just discussed that. It's given by this expression. All right?
Yes.
Okay.
Yes.
So then we say that this is, in any cases, is a function of theta and phi. All right?
Yes.
Then you do the expansions. What you expect that the two, in principle, that should be a summation of m from minus L to L. That should be L from 0 to infinity. And then you do have ALM of theta prime and phi prime. And then you have YLM of theta and phi. Do you agree?
Yes.
And the expansion is given in terms of YLM. Okay. And what I say to you is that due to the property of YLMs and due to the fact that this is a Legendre polynomial of order L, this summation will disappear. Okay. So it means that both of them, they have L values. Then you do have the summation of M from minus L to plus L, ALM of theta prime and phi prime, YLM of theta and phi. And what are the ALM? They are 4 pi divided by 2L plus 1, YLM star of theta prime and phi prime. There is no need for M prime. Essentially, there's the expansions that happens in that base.
Thank you.
Of course. Good. So let's look at a relationship which will be very important for us as well. Do you remember the green function? What was the green function? Was 1 divided by x minus x prime. This is one of the green function that we work with. And the property was that if you look at the Laplacian of this function, 1 divided by x minus x prime, that was given by minus 4 pi delta of x minus x prime. And no doubt that this is identical when you swap x and x prime. All right. So, and that appears in many different contexts that we work with. And one of the contexts that we work with was that if you assume that the charge distribution is localized, so we assume that is the charge distribution that we had, and we look at the infinity, essentially places which is large, and that's the charge distribution of x prime. And we consider that x is greater than x prime, okay? So we assume different scenarios when x absolute value is greater than x prime. So we are looking at far regions of these expansions. And in expansions, usually people, they don't use this word, and they say, hey, we consider that one of them is greater than the other one. And the one that is greater, we label it with R greater. And the one that this one is larger distance. And the other one is R smaller. Is okay. So, for example, if you look at the regions which they are really far away from the point charges or from the places that you do have a charge distribution, we call that X greater than X prime. Okay, and in this specific case, X is R greater, and X prime will be R smaller. Okay, it can happen in completely different contexts. So, for example, you may have a charge distribution where you are only looking at the regions which they are really, really close to the center. And the distances that you do have, that's for X prime. And you look at the regions which they are really, really small and close to the origin. Okay? And assuming that the charge distribution is on the boundary, for example, or is on a certain region. In that specific case, X prime is greater than the X. Okay, so the convention that we do have, it will be completely inverted. Is that clear? Depending on which region we are looking for. Can be far or can be way smaller than the charge distribution that we do have in the space. Okay. So 1 divided by X minus X prime, indeed, that is given by 1 divided by the value of X, which is R power of 2, the value of X prime, which is R prime power of 2, right? Minus 2R prime cosine of the angle between the two vectors, which in this case is gamma, cosine of gamma, power of 1/2. Do you agree with that? Agreed, guys? Okay, perfect. So, of course, this is an explicit expression, and as previously also we looked into this scenario. Now we can look at a different situation and see one of these two regions. Either X is greater than X prime or X prime is greater than X. So indeed, one of them is greater than the other one, okay? So I will label that with, because that is completely symmetric, I will write it in this way, is 1 divided by R greater, power of 2, plus R smaller, power of 2, minus 2R greater, smaller, cosine of gamma, power of 1/2. Do you have any argument with that? Do you agree? Indeed, it's symmetric. Doesn't matter if it's R prime or R. One of them is greater than the other one, and then we can do the expansion that we want. So if R greater is greater than, much larger than R small, then what we can do, we can factor off the R greater power of 2. Then what we will get 1 divided by R greater. Then it will be 1 plus R small, R greater, power of 2, minus 2 R small divided by R greater, cosine of gamma, power of 1/2. Okay. So indeed, what I have done, I assume that the larger distances can be factored out, and then we end up with this expression. Okay, So we can use the Taylor expansions. Indeed, this term, right, the entire this term that we do have is way smaller than 1 because we assume that R small is way smaller than R larger. So this means that this quantity is way smaller than 1. So this is look like epsilon for us. So it is 1 divided by R larger multiplied by 1 plus 1 plus epsilon power of 1/2. Do you agree? Because also cosine of gamma is bounded by 1 and -1, so it cannot be larger. Okay, so do the expansions. We will do the Taylor expansions. What is the Taylor expansion of that? Is 1 divided by R greater multiplied by 1 plus epsilon, of course, divided by 1 factorial. I don't write that. Epsilon power of 2 divided by 2 factorial plus epsilon power of 3 divided by 3 factorial plus other terms. Good? Assuming that epsilon is small. So let's do the expansions. Then it is 1 divided by R greater. Always we keep it with ourselves. The first term is 1. The second term is epsilon. What is epsilon? Is I think there is a mistake in the expansions. That is true for exponential. It's not true for that. Let me do that. So it's 1 plus epsilon power of n. So that will be 1 plus n epsilon plus n times n minus 1 divided by 2 factorial, epsilon power of 2, plus the other term. So indeed, that will be 1 minus 1/2 of epsilon, 2, plus minus 1/2 minus 3 divided by 2, epsilon power of 2, plus the other term. Is that right? Okay. The previous one that I have done, it was for exponential. Okay, so that was, that is now 1 divided by R greater, 1 minus 1/2 of epsilon, which the epsilon is R greater, R smaller divided by R larger, power of 2, minus 2 R smaller divided by R larger, cosine of gamma. That's the epsilon. The second term is minus multiplied by minus is plus 3 divided by 8, epsilon power of 2, which has the same expression. So it's R small divided by R great or large power of 2 minus 2 R small R great cosine of gamma power of 2 plus the other terms. Good? Is that fine? Let me see, what time is it now? Okay. So that will be 1 divided by R larger. It is 1. I will expand, I will set them together in such a way that the powers will be identical, okay? So now it is R small divided by R large. For me, that is the expansions power that I have to take care. So I will sort them together in such a way that the powers are identical. For example, this is the power of 2. And definitely power of 2 will be the second term, or the third term that I will keep. This is the power of 1. And then I will keep the power of 1 here. So it will be plus 2 goes away. And then it will be R smaller divided by R greater cosine of gamma. Okay. So that one is a power of 2. And look at the expansion. If you look at the expansions, the expansion will be R small r large power of 4 Then I do have the second term, which is minus 4 r small r larger power of 3 cosine of gamma. And then I have the second term, which is plus 4 r small r greater power of 2 cosine of gamma power of 2. Do you agree? So I have a power of 2 for the expansions of r's, and I have a power of 2 here as well, which I have to keep them together. And if you look at the other terms, they are power of 3, right? So the minimum power that you will get there is r small r greater power of 3. So which is beyond the expansions that I'm looking for, for it right now. So then I will get plus r small divided by r greater power of 2. Then the first term will be minus 1/2. And that term has a coefficient of 3 divided by 8. It has a coefficient of 4. So it will be plus 3 divided by 2 cosine of gamma power of 2. Plus r small r larger power of 3 and other terms. Agreed? Okay. So that will be 1 divided by r larger plus 1 plus, that is r small r larger. What is cosine of gamma? Is P1 of cosine of gamma. What is about the other one? R small r larger power of 2. And if you look at that term, is essentially P2. P2 of cosine of gamma. And I can also show the other term, which is r smaller r larger power of 3. It is P3 cosine of gamma. And other terms. And even that one, if you look at the expansion, essentially is r small r great power of 0, P0 cosine of gamma. Indeed, the entire of the expansions that I have is 1 divided by r larger, summation of L from 0 to infinity of r small r larger, power of L, PL of cosine of gamma. Okay, so indeed, the green function that I had, which was 1 divided by x minus x prime, and I know that one of them is larger, will be expanded in terms of 1 divided by r small, r larger, summation of L equal to 0 to infinity of r small r larger power of L, PL of cosine of gamma. Okay? Remember, that was the physics that we assumed. One of them was x, the other one was x prime, and gamma is the angle between these two. And I just used the addition theorem because I say that if you expand x and x prime in the spherical coordinates, if you do the x and x prime and expanding them in the spherical coordinate, they will be function of theta phi, theta prime, phi prime. Then you can use the addition theorem and expanding PL of cosine of theta in terms of summation of m from minus L to L. All right. Then I had a coefficient which was, I think was, let me look at the expression, guys, was 4 pi divided by 2L plus 1, YLM star of theta prime and phi prime, YLM of theta and phi. Okay, remember that comes from the addition theorem. You can keep it like this. There is absolutely not a problem. This is a further step just to show to the people that, hey, one can use the spherical harmonics which they are complete bases, they are orthogonal bases, and expanding the green function in terms of YLMs. So, and indeed, that is what we will get. It is 1 divided by R larger, divided summation of L from 0 to infinity. Is not surprising, you will see. Summation of M minus L to L. Then what I have is 4 pi divided by 2L plus 1, R smaller, R larger, power of L, YLM star, theta prime and phi prime, YLM of theta and phi. All right. So what I have done so far, in spherical coordinates, I expanded the green function in terms of YLM and also R power of L. You will see that. R power of L, R power of L plus 1 in the denominator. Okay? Is that clear? Questions? Tarek? No? Okay. I thought that you have a question. As an exercise, do the same expression and expansion for Bessel functions in spherical, cylindrical coordinate, because they are complete bases. The phi, e power of im phi is complete base. Jm of k rho is complete base. So try to do the expansion of 1 divided by x minus x prime in terms of Bessel functions and spherical harmonics. Good? Can someone tell me, definitely the expansion in this coordinate, it gives you these L and M, which is summation. What are you expecting for Bessel function? It will be a summation? We just discussed about that at the beginning of the lecture.
So Bessel functions have like the form of summation. So maybe the expansion.
Was it summation or was something else? Was integral. So if you do the expansion in cylindrical coordinate, for M will be a summation, which is on the integer quantity. But when it comes to a radial part, it will be an integral, okay? Because you have to do the integral of rho, d rho, and then this is jm k rho. So essentially, in the expansions that you need to do, it will be integral of k dk jm of k rho, okay? That is what I'm expecting to appear in the mathematics. So do this as an exercise. We have previously looked into the mathematics. Okay. Any questions so far? Beautiful. So now let's look at an example. And the example that we do have is a sphere. I assume that I have a sphere, which the sphere is grounded. And I'm looking for potential any places outside of these region. Okay. So we got this sphere. The green function that we had was 1 divided by x minus x prime. That was the green function. All right. And with the sphere, which is grounded, we need to find f of x and x prime, which allows us to satisfy the boundary condition. Okay. And in order to find that, I mean, I look at the sphere, and what is known for the sphere is the potential at the boundary. Then the choice that we had was going with the Dirichlet boundary condition and finding the solution. So how did we solve the problem? We assume that we have a charge here at the distance of, I don't know what I have chosen. I don't remember, honestly. So the sphere radius was A, and that distance?
It was Z naught, I think.
Z, okay, fantastic. And tell me.
It was Z naught, like.
Oh, Z naught, okay.
Yeah.
Okay. And then we say that if the charge is Q, then the charge of Q prime will appear here at the distance of Z prime, right? And we did the mathematics, and what we found out, I'm just looking at your book if I can find inside of your book what was the result for this. Oh gosh, your book, classical electrodynamics. Mm-hmm. It's chapter, I think we solved that in chapter 2.
Chapter 2, yeah, and the distance.
Okay, so I'm looking at the result that we had. I think, oh, we got that, yes, I found this. So then this expression was given by 1 divided by x minus x prime plus, minus, sorry, for sure is minus because the charge that you will get in mirror one, it's A divided by R prime, then that was x minus A power of 2 divided by R prime power of 2 and x prime. Okay, we got that. So that was what we found due to the image charge. And that was for Dirichlet boundary condition. We solved that previously, and I think a more complicated one was given for you, given to you for your midterm exam. So, okay, fine. So far, we have no problem at all, and we find a green function. Now, the point is that this find the green function in terms of spherical harmonics and see what we will get from the spherical harmonics in terms of expansions. Okay. Yeah. So that is what we expect. Good. So we already did the expansions for the first part, which is this expression. So 1 divided by x minus x prime. We did expansion, and that is 1 divided by R larger and summation from L0 to infinity, summation of M from minus L to L plus L. And then I have 4 pi divided by 2L plus 1. and then I have R smaller, R larger, power of L, and then I have YLM of star of theta prime and phi prime, and then YLM of theta and phi. The same expression also can apply, and it's the same solution also can apply for expanding A divided by R prime x minus A power of 2 R prime power of 2 of x prime. You can do exactly the same expression. So A divided by R prime is here. Then I assume that R is greater, so it's 1 divided by R greater, summation of L from 0 to infinity, summation of M from minus L to L, then 4 pi divided by 2 L plus 1, then R greater R small, that will be A power of 2, that is R prime goes away, that will be divided by R prime power of L, YLM star of theta prime and phi prime, YLM of theta and phi. So that I assume that is R small, okay? That is R larger. So R small essentially is A squared, R prime divided by R prime power of 2, and R is the R great. And if you do the expansions, you will get exactly this expression that we discussed. So the green function that I'm expecting for this geometry is given by 1 divided by R. I'm assuming that the far distance, because we assume that we are not looking inside of the sphere, we are looking outside of the sphere, is summation of L from 0 to infinity, summation of M from minus L to plus L. Then I do have 4 pi divided by 2L plus 1. And then we do have expression for R part, which for the first one is R prime divided by R power of L. For the second part is minus A divided by R prime, then A power of 2 divided by R prime power of L, then YLM star theta prime and phi prime, YLM of theta and phi. That's the green function that I'm expecting. Okay. Now, I'm looking at your books and I find exactly the same expression. Okay, so indeed, this is the green function that you are dealing with. So you can replace it, you can take the derivative, you can replace it inside of the boundary condition that we had, which was integral of the green function or derivative of green function in your calculations. So the key point here is that indeed, any functions that you do have can be expanded in terms of, let's say, complete basis. In spherical coordinate, it's spherical harmonics. Even you can solve, let's say, the green green differential equation in terms of that, and then and replacing inside of the green theorem, the second green theorem, and finding the potential everywhere that you are looking for. So I will stop here because I know that maybe it was too much. And after that, we will come back with, if you want, I can teach you also how to use it inside of the differential equation for the green function, or we can go with the multiple expansions of charges. So let's have a 10 minutes or 12 minutes of break, and then we will see each other in about 12 minutes at 4. So recording, guys. While I mean, we had a couple of funny and interesting discussions. So while it was not recording, Nazanin asked that why we are doing these sort of expansions. I mean, of course, this is beautiful. Is just fancy, right? I'm translating your question, Nazanin. Maybe it's not a proper translation. Of course, this fancy is nice. The green function is expanding in terms of harmonic, spherical harmonics, and it's beautiful. But we knew the green function. It was just here. Why we are doing that? Okay, let me go back and saying that, look, I'm giving you a geometry. Okay, this geometry was such a way that I could solve it easily. Now I will give you a geometry, which the geometry is more complicated. So I will give you a spherical geometry of the spherical cylinders, and then maybe another cylinder at the distance of A and distance of B, right? And I do have different boundary conditions there. And I'm asking you to find the potential inside, outside, between the regions. I can give you this question, right? And maybe the cylinders are kept at different potentials of, let's say, V0, or maybe I don't know, V prime or V1. And then maybe there is a charge distribution around that. And then I'm asking you, find the potential here, find the potential here, find the potential here. This is a question that I can provide you. The only things that you know that for any charge distribution that you may have here, you have to find the green function. What are the green function? It's a function of x and x prime. What do you know about this? It's symmetric, first of all. Second is that Laplacian of g of x and x prime must be equal to minus 4 pi delta of x minus x prime. All right? This is the only thing that you know about that. Nothing more than that. What is the symmetry here? It's spherical symmetry. Then you expect that it will be expanded in terms of theta and phi and r as well. So what you are expecting for g of x prime, and we know that x, of course, will be given in terms of r, theta, and phi, and the same situation for x prime, which will be in terms of r prime, theta prime, and phi prime. Then what you do, you want to solve this green differential equation in that specific coordinate. So what are the bases now? We know very well that the solid angle, theta and phi, they form complete bases. What are the complete bases that we are using? Is YLM of theta and phi. All right. But the only problem that we don't know, which is essentially, it comes from the symmetry that we do have, is that we don't know what is going on with the radial part. The only part that about the potential that we don't know is the radial part. All right. So what do you do? Then you say that the delta of x and minus x prime, that can be expanded in terms of the variables that I do have, which is delta of, if you remember, I did the expansions in spherical coordinate, in cylindrical coordinate, in Cartesian coordinate, we did the expansions. For example, for Cartesian coordinate, that was x1 minus x prime 1, delta of x2 minus x prime 2, delta of x3 minus x prime 3. And for spherical coordinate was 1 divided by r squared, delta of r minus r prime, delta of phi minus phi prime, and delta of cosine of theta minus delta of cosine of theta prime. Okay. All right. Clear? So indeed, but this is what I'm going to do. I will say that, okay, Laplacian of g of x and x prime that is given by minus 4 pi, the delta. So what is the delta here in spherical coordinate is 1 divided by r squared, delta of r minus r prime, delta of phi minus phi prime, delta of cosine of theta minus cosine of theta prime. All right. Now, I will say to myself that this part is essentially, it can be expanded in terms of spherical harmonics, all right? Because this is the completeness relationship that you do have between the phi and phi prime and theta prime. So that can be replaced by summation of m from minus L to plus L, L from 0 to infinity, and that is nothing more than YLM of theta and phi prime with a star, YLM of theta and phi. Do you agree? So indeed, the expression that we do have now is 1 minus 4 pi divided by r squared, delta of r minus r prime, summation of L from 0 to infinity, summation of m from minus L to L, and that is YLM theta, theta prime, phi prime, and YLM of theta and phi. Do you agree? All right. This comes from the fact that I know how the delta can be expanded in terms of spherical harmonics. And in addition, what else I know is that, look, I have to solve this equation in any cases in spherical coordinates. How can I solve them? You have to write the Laplacian, which actually was Tarek's question, in spherical coordinates. So what is the Laplacian in spherical coordinates? I don't remember. I have to look for spherical coordinates. Laplacian in spherical coordinates. I can drive it, but I don't believe that we do have time. Okay, so Laplacian that we do have it in cylindrical coordinate is 1 divided by r squared, derivative with respect to r of r squared, derivative with respect to r, plus 1 divided by r squared, 1 divided by sine. What's that? Okay, phi, okay. Derivative with respect to theta. Then I have 1 divided by sine of, it sounds a little bit funny for me. Let me look at it. Okay, so I understand completely that it's funny because that should be sine of theta, derivative with respect to phi, theta, derivative with respect to theta, sine of theta, derivative with respect to theta of the argument. Okay, that's the derivative that I do have. What I know about the g of x and x prime, that is essentially what I'm looking for. I can do the separation of variables, right? What are the solutions for the radial part? I don't know, because that's a problem for me. As soon as I know the solution for the radial part, then this problem is solved. What are the solutions for the azimuthal and theta part? Spherical harmonics, nothing more than that. So indeed, the g, x, and x prime is nothing essentially more than the expansions in terms of L from 0 to infinity, summation of m from 0 to m minus L to L of a coefficient, which we'll be discussing about that, YLM of theta and phi. All right. And the coefficient indeed is given by ALM, and it's function of R and R prime, no doubt, and theta prime and phi prime. Okay. And we know very well from the addition theorem that this is essentially nothing more than the coefficient that we discussed. I mean, previously we discussed about that, but it's something like GL of R and R prime and YLM star of theta prime and phi prime. If you remember, if you did the expansions of cosine of gamma or PL of cosine of gamma, and if you do the expansions, then what you get in terms of expansions coefficient, it was just only YLM theta and phi, YLM star theta prime and phi prime. The only difference is here is that you do have the functionality and additional functionality, which is function of R and R prime. And that is only depending on L, not M. Okay? Okay, fine. Now, from one side, we get this expression. From the other side, I know that g, x, and x prime can be expanded in terms of this expression. Substituting inside of this equation, I will get the following expression, which is 1 divided by r, d dr of r, second derivative, of course, because a second derivative of r, gr and r prime minus L times L plus 1 divided by r squared g L of r and r prime equal to minus 4 pi divided by r squared delta of r minus r prime. Okay, so if you substitute g inside of the equation, and you know from the other side that also YLM, they form complete basis. So essentially multiply both sides by YLM prime, theta and phi, and doing the integration on d omega, then you will get all expressions simplified because they are orthogonal basis. Then the only part that is remaining as a puzzle to be solved is the radial part, which is this equation. Okay, how can you solve this? Depending on the boundary condition that you do have. What are the boundary conditions that you do have? You have 2 boundary conditions, you have 3 boundary conditions, you have 4 boundary conditions, or what else? At 0 is undefined, or at infinity is going to be 0. So those are the conditions that you have to apply, and from these conditions you will get GL of R and R prime. All right? Is that clear? The same story happens when you deal with cylindrical coordinate. If they give you, let's say, some sort of boundary condition which they hold the cylindrical symmetry, and they are asking you to find the green functions, you will go exactly in the same fashion. In that place, you have to expand them in terms of e power of I and phi, and Bessel function, which is Jm and Nm, right? In both Bessel functions, the first kind, the second kind. You have to expand them, and then you will get the solution that you want. You can look at the, I think, last section of your book, and you will find a couple of examples which Jackson solved the equation in this way, finding what are the relationship that you need to solve these differential equation for a few boundary conditions. Clear? Good. Any other questions, guys? Okay. So now let's go back to the lecture, and indeed, there are a couple of points that we want to follow and we want to understand, because honestly speaking, the physics is beautiful, and as a physicist, we usually use approximation, and we usually use certain basic conditions to find and having a feeling about the physics of a system, or understanding the physical property of a system. Let's go back to the charge distribution. And even this charge distribution can be with boundary conditions. It's up to you guys. And what do we have? We define them to be localized. So they are in a certain region in a space, which I call it X prime, including the boundary condition, remember. So it may have, let's say, certain boundary conditions here. And then I'm looking at the physics at infinity, or regions which they are really, really far away. So X is greater than X prime. Okay. Let's solve these for two different cases. One in cylindrical coordinate, one is in spherical coordinates. Let's do that and see what we will get as a potential in that place. So if the charges are localized, then within the first approximation, we will get that potential is given by rho of X prime, d3 X prime divided by X minus X prime. Do you agree with that? Okay, that's only due to the charge distribution. Of course, we do have the boundary condition issues, which we neglected so far. We say that that's with the green function, and or the surface is excluded because we are going really far away. And if you go far away, then that can be neglected. And the rho of X prime, we cannot do any approximation on that. The only term that we can consider and give a fight between X and X prime is the dominator. Okay, so 1 divided by X minus X prime is the only term that you can compare observation field distance and the charge distribution place. Observation point distance and the charge distribution length, or you can have it in terms of volume. So I can give a fight between the volume that I have it for the charge distribution and the far distances. All right. 1 divided by X minus X prime. Which coordinates do you choose for the expansions? Because now I have to compare X and X prime. And I assume that X is greater than X prime, then I have to do the expansions. So which coordinate do you do? Do you prefer to consider spherical coordinates, Cartesian coordinate, cylindrical coordinates? Let's go with easy way, because you have a feeling about that. Let's go with the Cartesian coordinate first, because we have not done. Spherical coordinate is just a replacement, we can get it. So let's do it in Cartesian coordinate. So what does it mean? This expression is 1 divided by x minus x1 minus x prime 1 power of 2 plus x2 minus x prime 2 power of 2 plus x3 minus x prime 3 power of 2 power of 1. Look, the point of observation for us is the important part. So that's the expansion it has to be done in that term. So is a function of x1, x2, and x3. This is very, very clear. Or let's do the expansions in terms of x prime 1, x prime 2, and x prime 3. This is also another option that we have to consider. And this is a f of this, function of this. How do you do the expansions of multivariables function? Let's go a step back. How do the expansion of x prime? F0, right? Plus x prime divided by 1 factorial f prime of 0 plus x prime power of 2 f second of 0 divided by 2 factorial plus the other terms. This is a Taylor expansion. How do you do the expansions for a function which has 3 variables?
Just use partial derivatives?
Yes, excellent. How?
Like instead of just in terms of x, in terms of the separate ones. But would you then have to like keep the, like, would it be a Jacobian sort of thing? Or a Hessian?
You can do with that. I would go simple. I will go simple. Yes.
Is it in like a gradient? Like.
Yes, exactly. It goes with the gradients.
Oh, that makes no sense. Okay.
Yeah, sorry. If you say that, I missed that, Gavin.
I definitely didn't, but no, that makes way more sense.
So indeed, you will go, I mean, the first thing is that you can do the expansions on x in terms of x prime 1. You can do the expansion in terms of x prime 2. You can do the expansion in terms of x prime 3. Okay, doing them in sequence, but then you can factor or you can gather all together, and what you will get the following one is f of 0, 0, and 0. That's the first term that you will get. The second term that you will get is summation of xi, derivative with respect to xi of f at xi equal to 0. I is changing from 1 to 3, okay? The second term will be 1 divided by 2 factorial, or the third term, will be summation of xi, xj, second derivative of f with respect to xi, second derivative of xj, at xi, xj equal to 0, and plus other terms, okay? This is what we will get. All right, and as you pointed out, some people, including myself, I would prefer to write it in this way. I will write it in terms of x dot nabla gradient divided by n factorial power of n acting on f at x equal to 0 and changing from 0 to infinity. This is the compact form. You can do the expansions. N equal to 0, that will be f0. N equal to 1, that will be x dot nabla. Okay. So I can do the expansions. The first term will be f0. The second term will be x dot nabla acting on f divided by 1 factorial. That one, the other one will be x dot nabla power of 2 acting on f 2 factorial. If you do the expansion of these, it will be x derivative with respect to x plus y derivative with respect to y plus z. Or let's say, I have not used that notation. That will be x1 derivative with respect to 1 plus x2 derivative with respect to 2, x3 derivative with respect to 3. Okay. And remember that always nabla will act on f, so it will not act on x. So it's on the right side. Good. Are we good? Okay. So let's take the derivative. So what we do have is 1 divided by x1 minus x prime 1 power of 2 plus x2 minus x prime 2 power of 2 plus x3 minus x prime 3 power of 2 power of 1/2. This is the function of f which we are looking for, and now I'm doing the expansions. The first term, which is f0, which is x prime 1, x prime 2, x prime 3 is equal to 0. What it will be the result? Will be 1 divided by x1 power of 2 plus x2 power of 2 plus x3 power of 2 power of 1/2. What's that? This is equal to 1 divided by r, which is that distance, is this distance. All right? 1 divided by x squared plus y squared plus z squared. Is that clear? I don't see the okay from all of you. Okay. Now look at the derivative of f with respect to one of the arguments, one of the parameters, which can be x1, x2, or x3, x prime 1, x prime 2, or x prime 3, one of them. So go with one of them. X prime 1, is that fine? Okay, let's go with that. So if you take the derivative, it will be minus 1/2, then it will be 2 times x1 minus x prime 1. And there is a minus sign because I'm taking the derivative with respect to x prime. Okay? Divided by whatever I have in a denominator, power of 3 divided by 2. All right? Good, beautiful. I can write that also in a general fashion. I can say the derivative of f with respect to any x prime I is, the 2 goes away, minus sign goes away. It will be x1 or xi minus x prime I divided by denominator power of 3 divided by 2. Good? That is true for x prime 1, x prime 2, and x prime 3. If I take the derivative of f with respect to x prime I at x prime equal to 0, it means that any x prime 1, x prime 2, and x prime 3, that will be equal to 0. So it means that on the numerator, only xi will remain. On the denominator, only r will remain. So it will be xi divided by r power of 3. Good, guys, are you following? Good. Any questions? The tricky part is, I mean, look, this is the first coefficient, this is the second coefficient or expansion term. Now the last one, which is the third expansion, is the second derivative of f with respect to j I. What does it mean? that taking the derivative of the above expression with respect to x prime j. So it means that taking the derivative of this expression with respect to x prime j. This is what I'm doing. Xi minus x prime j. Denominator power of 3 divided by 2. Okay, so it is two terms. First, I have to take the derivative of numerator, multiply by the other term, and then plus the derivative of denominator and multiplying by the other. Okay, so let's do the mathematics. It's two functions. So the first derivative will be derivative of xi minus x prime I with respect to x prime j. What it will be the result? Exactly, it's a delta function. It will be minus delta of ij. Because derivative of xi and xi with respect to x prime j, it's 0. Derivative of x prime I with respect to x prime j is 0 unless I is equal to j. When is equal to j, that will be 1. Okay, perfect. Divided by denominator, which denominator is again 3 power of 2. It has, remember, it has x1 minus x prime 1 power of 2 plus x2 minus x prime 2 power of 2 plus x3 minus x prime 3 power of 2. Okay, don't forget that. What about the derivative of other one? So it will be plus xi minus x prime I. That remains. Now I'm taking the derivative of denominator. So it will be minus 3 divided by 2. All right? Because it's the power. Then inside of that, I have minus 1 multiplied by 2 multiplied by xj minus x prime j. Exactly look like what I have done here. The only difference is that the denominator now is power of 5 divided by 2. Good? Clear? Perfect. So let's simplify this. The 2 goes away with 2. So it will be, let's just substitute it directly because I don't need this expression. I'm not going to take another derivative. It will be second derivative of f with respect to x prime I or x prime j, x prime I at x prime equal to 0. That will be minus delta ij divided by r power of 3 plus, yes, because that goes away, 2 goes away, 3 xi xj, because x prime I and x prime j, they will be equal to 0, divided by r power of 5. Good? Is that clear? Beautiful. Remember, that's only the part of the expansions that we do have. I have to now replace it inside of the expansions. So expansion means that one, guys. This expansion. I have to one by one substituting there. So what does it mean? I will write it down. So we have 1 divided by x minus x prime. This is equal to f0 plus f prime 0 divided by 1 factorial times the summation of I from 1 to 3 xi, sorry, x prime I, that, sorry, my bad, derivative with respect to x prime I of f at 0 plus 1 divided by 2 factorial x prime I, x prime j, second derivative of f, x I, x prime j, plus the other term. Okay, is that fine? Then now let's substitute it. The first term will be 1 divided by r. The second term will be 1 divided by 1 factorial. It will be x summation of I from 1 to 3, xi x prime I divided by r power of 3 plus 1 divided by 2 factorial summation of I j x prime I x prime j. Then what I have also is r power of 5, 3xi xj minus r power of 2 delta ij plus the other term. Good. Any mistakes? Good. That's the expansion in the Cartesian coordinate. Indeed, why I have done that, because I want to look for the potential at the position of x, which is 1 divided by 4 pi epsilon naught, integral of rho of x prime divided by x minus x prime, d3 of x prime. And now I have done the expansions, so it means that I will get rho of x prime multiplied by all of these terms, 1 divided by r plus xi x prime I from 1 to 3, that is nothing more than x dot x prime, right? Divided by r power of 3 plus 1 divided by 2 factorial. That term has a little bit of complexity, but I will keep it in the same way. Ij, x prime I, x prime j, 3xi xj minus delta of ij r power of 2 divided by r power of 5 plus the other term, d3 of x prime. So then I will get 1 divided by r, or should I keep it inside? I don't remember really the notation that people, they use it, but let me look at that. Yes, that's good. Go with this way. It will be 1 divided by 4 pi epsilon 0. Then I have 1 divided by r, integral of rho of x prime, d3 of x prime. That's the first term, right? Plus the second term, 1 divided by 4 pi epsilon 0, 1 divided by r power of 3. X will be outside of the integral because integral depends on the x prime, dot integral of rho of x prime, x prime d3 of x prime. Remember, this is a vector, right? You have to do the mathematics and doing the calculation of rho of x prime, x1, x prime 1 integral. Rho of x prime 2 integral, rho of x prime 3 integral, or in terms of x prime, y prime, and z prime. You have to do the mathematics and finding that. The outcome of that will be a vector. Okay. What about the third term? It is 1 divided by 8 pi epsilon 0. 1 divided by r power of 5 is a summation of I and j, is on 2 indices. Then it will be 3 xi xj minus delta of ij r power of 2. All right, good. Then you do have another integral, which is integral of x prime I, x prime j, rho of x prime d3 of x prime, plus another term, which definitely you have xi, xj, xk. So it's 3 indices, and you have to do this summation over all of them. Let's look at the physics first, and then we will simplify. Also, we need to work a little bit on this term and writing it in a proper way, in such a way that you will find it in other books, and there is a reason behind of that. Okay, so let's look at the first term. What is this? Integral of rho x prime d3 x prime.
Total charge.
Exactly, this is total charge. What about this one? Let's write it down. It is integral of rho of x prime d3 x prime, or integral of rho of x prime y prime d3 of x prime, or integral of rho of x prime z prime d3 x prime. I wrote it in terms of x prime, y prime, and z prime in such a way that you can understand it better. This dipole moment, right? This dipole moment is the charge multiplied by the distance. Clear? So this is monopole term. This is a dipole term. Look at that term. Essentially, if you look at that term, is getting a little bit more complicated. It's not only look like a vector, because I mean, this one, if you look at that term, it's a vector. It requires to be calculated for x prime 1, x prime 2, x prime 2. So it's a 3 vector, which we call it with a p. Okay, it will be x dot p. But if you look at that term, the yellow-ish highlighted with the yellow it requires 2 indices. So if you look at that term, essentially it has two indices, and is not look like a vector. Is a tensor. Is a tensor of rank 2. Okay, and usually people they like it with a Qij, but before doing that, I have to do a little bit of simplifications and showing to you that it can be simplified further. Okay. Because no one really looks at x prime I, x prime j, and showing to you that that's a quadrupole, what they call a quadrupole tensor. So right now, guys, remember this is the expansions that I do have, and I will come back to the physics and we will discuss about the physics behind of these. But now I'm only concentrating on the quadruple term and I want to simplify this. I don't care about the coefficient, I only pay attention to the summation. So what I deal with is the summation of ij, 3x prime I, xi, xj minus delta of ij r power of 2 times integral of x prime I, x prime j, rho of x prime d3 of x prime. Good? I want to make it symmetric. What I do, I will multiply both sides by a 3. So I multiply the denominator by 3. I will put a coefficient of 1 divided by 3. Is the same, guys? Do you agree? Okay. What I'm going to do, I'm going to make these to be completely symmetric in terms of xi and x prime I. So I want to make it symmetric in that way, in this fashion. So the 3 appears here, so it's very similar to that one. What I need to do, I need to add an r power of 2 prime delta of ij. When I subtract these r minus r prime power of 2 delta of ij, I have to multiply, I have to add another term, which is r prime power of 2 delta of ij. I'm manipulating it such a way that it will be identical, but I end up with an additional term, which this additional term is r prime power of 2 delta of ij. Okay, so then that will be 1 divided by 3, summation of ij, 3xi, xj, minus delta of ij, r power of 2, integral of 3x prime I, x prime j, minus r prime power of 2 delta of ij, rho of x prime, d3 x prime. But I have an additional term. What is this additional term? Plus 1 divided by 3 summation of ij, 3x prime, xi, xj minus delta of ij, r power of 2, integral of r prime power of 2, delta of ij, rho of x prime, d3 of x prime. Do you agree with me, guys? Now, this term is symmetric, as I expected, and I'm happy with that. The only problem that I have is this term, is an extra. And let's see what it will be the result. So delta of ij is independent. It will go outside of this integral, okay? So what I will end up, it will be summation of ij, txi, xj, delta of ij minus delta of ij, r power of 2. And there is another delta of ij. Good? So two summations are there, on I, on j. Whenever I is not equal to j, all of those terms are 0 because of the delta ij. When I is equal to j, then that term becomes r power of 2, and that term becomes 3xi power of 2. And still there is a summation here, which is remaining. Do you agree? Do you agree on that? Okay. Now let's do the expansions. The tx1 power of 2, x2 power of 2, x3 power of 2. What is that? 3r squared. What about the other term? Is summation of r power of 2, but 3 times. It is minus 3r squared. What is the result? Is 0. So indeed, the entire base is equal to 0, and we made it symmetric without changing anything. So essentially, If you want to do the mathematics, honestly, if you want to calculate the quadrupole calculation, the only factor that is playing role is this 1 divided by 3, which appears in the calculation. If you forget about that, it's just calculate xi, xj. That's all. Okay. So now I will write what is going on. So the quadrupole term is 1 divided by 8 pi epsilon 0, 1 divided by I power of 5, summation of ij, 3xi xj, minus delta of ij, r power of 2. And then I have an additional 1 divided by 3, which is appearing here. And then I have integral of 3xi xj prime minus r prime power of 2 delta of ij rho of x prime d3 x prime. Remember, this, since I created this 3, 1 divided by 3 is needed. Okay? What we call this? Qij is what they call it, the quadrupole term. And Qi, let's write it down. So help me, guys, because I'm sure that I will do mistakes. But with your help, we will be able to write it properly. So phi of x, indeed, which was 1 divided by 4 pi epsilon 0, integral of rho of x prime divided by x minus x prime, d3 of x prime. Now, approximately is given by 1 divided by 4 pi epsilon 0, q divided by r, right? Plus 1 divided by 4 pi epsilon 0 x dot p divided by r power of 3 plus 1 divided by 4 pi epsilon 0, 1 divided by 6 as well, summation of ij, 3xi xj minus delta of ij, r power of 2, qij divided by r power of 5, plus the other term that I have not written. Q was a monopole term, which was integral of rho of x prime d3 x prime. P was dipole term, which is x prime, rho of x prime d3 x prime. And the quadrupole term, which is qij, was given by integral of 3 of x prime I x prime j minus delta of ij r prime power of 2, rho of x prime d3 x prime. Okay. Interesting. So assuming that we can be far away, the charges are localized. So if I have this espresso mug and is charged, then if you go far away, what you will see, either you will see it as a point charge, which is look like the first term, which is q divided by r, 1 divided by 4 pi epsilon 0. Or if the net charge is 0 for any reasons, then you will see the dipole term, which means that the potential is going to be 1 divided by r power of 3 x dot p, okay? which that's a dipole term. It may happen that even the dipole term is 0, then what you will see the quadrupole term, which appears as r power of 5 in the calculation. Don't get confused. The potential doesn't go to be 1 divided by r and suddenly jumps to 1 divided by r power of 3. Okay? Look at the potential. It is x divided by r power of 3. So if you look at the dimensionality, it will be 1 divided by r power of 2. If you look at that one, that is going to be x times x divided by r power of 5. That will be r power of 3. So essentially, this is order of 1 divided by r. That's order of 1 divided by r power of 2. That's going to be r power of 3, and etc. Okay? So remember, that's the expansions that people are looking for. And depending on which term appears, you can cut the series there. If the monopole is there, monopole is important, you have to keep it because it's beating the other terms. If monopole is vanishing, but the dipole term appears, then you can even neglect the quadrupole term. They may have contribution, but not significant. If the dipole term still is vanishing, and then you go to the quadrupole and quadrupole appears, then you have to take care of the quadrupole and octupole and etc. Okay? So that's a contribution. For example, I can give you a certain charge distribution and see what we will get. So if you have a point charge like that, Q, definitely at the far, the monopole charge is important. True, guys? This is what we know. What about this one? I keep them in the distance of A together. Monopole charge is 0, the sum of these two within first approximation. Then you have to go to the second term, which is the dipole term. The dipole term plays role. So if you're far away from these, then you will get only the dipole term. Look at this one. The distance between them is A. I keep it in a square. So it's plus Q minus Q plus Q minus Q. If you look at the dipole in any direction, is 0. Because it looks like one dipole in the upper side, one dipole in the lower side. So if you look at that, is canceling out each other. The same fashion, if you look at that, these one dipole like that, another dipole like that, is canceling out each other. So any direction that you watch, the dipole term is vanishing, then the only term that plays role is the quadrupole term. And for this set of geometry. Looking at another one, look, I'm giving you another puzzle. Okay. This is Q. This is minus Q. The distances are the same, so I will not write it down anymore. Q minus Q. And then I will put it on a cube. And the cube here, 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 and here, they have this charge distribution. Q minus Q, Q minus Q. And if you look at that, monopole is 0, dipole is 0, quadrupole is 0, then you have to go to the other one. You have to calculate Tijk, okay? And then that tensor of rank 3 is not 0 anymore, and it keeps that, okay? So with this way, most of the time, we can understand that what are the most contribution that you may get from a charge distribution, either deep solving the equations and finding the green function and charge distribution, etc. So from the symmetry, essentially, you will get the solution. You will get the physics, the feeling about the physics. And what I have done so far, I looked only at the Cartesian symmetry. These are, if you look at all of them, they are Cartesian symmetry. I can do the same situation for spherical and cylindrical coordinate as well. Let's do that, okay? Is that good? Any questions? We have about, let's say, the 12 minutes, and I will go to spherical one. Fantastic. So the only things that I have to do to solve the problem is going and doing the expansions in terms of spherical harmonics. So indeed, the starting point that we had was potential (1 divided by 4 pi epsilon 0) integral of rho of x prime divided by x minus x prime d3 x prime. The only things that we have done was looking at the 1 divided by x minus x prime and expanding things in terms of in the Cartesian coordinate, assuming that x is way bigger than x prime, and that was the expansions that we have. We can do the same situation with spherical harmonics. So we already did that. We assumed that one of them is larger than the other one, and the expansions was 1 divided by r greater, right? And then we had summation from L from 0 to infinity, and then we had r smaller, r greater, power of L, PL of cosine of gamma. And the gamma was angle between the two x and x prime, between the two. And then we used the additional theorem and addition theorem. And using addition theorem, we expanded this in terms of only m value, which is changing from minus L to L. And that was, I think, 4 pi divided by 2L plus 1. And indeed, was YLM star of theta prime and phi prime, and YLM of theta phi. So indeed, the entire of this expansion will be 1 divided by r larger, L from 0 to infinity, M from minus L to L, R smaller, R greater, power of L, 4 pi divided by 2L plus 1. And then I do have 1 YLM star of theta prime and phi prime, YLM of theta and phi. All right? And we already tried that, essentially. So the only things that I have to do, I have to substitute these expansions inside of the potential, which is localized, for the localized charge. So phi of x indeed will be 1 divided by 4 pi epsilon 0 integral of rho of x prime 1 divided by r greater summation. And we assume that r is greater than r prime. So we know that then in this calculation, that will be r. And that will be summation on L from 0 to infinity, summation from M from minus L to L. That will be R prime divided by R power of L, 4 pi divided by 2L plus 1, YLM star of theta prime and phi prime, YLM of theta and phi. And remember, the entire of these should be multiplied by D3 x prime, which D3 x prime is the volume. So you have to multiply it by r squared, the omega. But let's go in this way, sorry. It will be r prime, dr prime, d omega prime. Good? That is essentially d theta prime, sorry, d phi prime, d phi prime, d of cosine of theta prime. Any questions so far? So good? Okay, fantastic. Let's go and see what else can we do. So the summation will be out L from 0 to infinity, summation of M minus L to L. Four pi goes away. I do have 1 divided by 2L plus 1, 1 divided by epsilon naught. I do have YLM of theta and phi. We do have R, 1 divided by R power of L plus 1. We do have R prime power of L, YLM star of theta prime and phi prime, D3X prime. The charge distribution, sorry. Rho of X prime, D3X prime. All right, I cannot take the integral out of this summation. Remember, because that depends on L, depends on L and M. Remember, the functionality of phi and the dependence on theta prime and phi prime is here with R prime as well. The rest, they are independent of R prime, theta prime, and phi prime. All right. So that will be summation on L equal to 0 to infinity. Look, how do I cast them? It's 1 divided by 2L plus 1. Okay. 1 divided by epsilon is really not important. It's a scale, which I can place it even outside. It's up to you. In the definition, maybe is important. What I care is 1 divided by R power of L plus 1, or maybe I have to write it in this way. Sorry, guys. 1 divided by R L plus 1. Then I do have YLM theta and phi divided by 2L plus 1. And then I have integral of R power of R prime power of L, YLM theta prime, phi prime, rho of these. The entire these, we maybe with 1 divided by epsilon 0, I call it QLM star. Okay, so the entire of this integral with 1 divided by epsilon 0, I will call it QLM. I don't believe that in your book they use 1 divided by epsilon 0 also in the calculation. Let me go to check out your book. No, they don't use it. So 1 divided by epsilon 0 is just a scaling factor that it is a unit that you have to handle it. That's one reason that I love CGS units, because electric field and magnetic field, they are the same. And there is no 1 divided by epsilon naught or mu naught in the mathematics. Okay, so that's the expression that we receive it, okay? So far, so good? course, there's a m from minus infinity, minus L to plus L. QLM indeed is defined as integral of r prime power of L, YLM, theta prime, and phi prime, rho of x prime, d3 of x prime. We call these also multi-pole expansion. Exactly look like what we have done in the Cartesian coordinate. Why we can look at that? Look at the potential, right? First of all, the magnitude, let's say, or the strength of the potential, according to our functionality depends on R, is going to be only R power of L plus 1. Okay? So if you look at that expression, you will see that it goes to be 1 divided by R power of L plus 1. There is no functionality on M there. Okay? Is that clear? So if L is equal to 0, for L equal to 0, that will be 1 divided by R. For L equal to 1, that will be 1 divided by R power of 2. For L equal to 2, that will be 1 divided by R power of 3. So that is what we call it monopole contribution, dipole contribution. That also is a quadrupole contribution, and etc. Okay, exactly look like Cartesian coordinate. Monopole has only one term because L is equal to 0, therefore M also is 0. Because if you set L equal to 0, then M will change from 0 to 0, which is essentially 0. So the only contribution that you will get here is Q00. If you do the mathematics, it's easy to be handled. For L equal to 1, we do have 3 contributions, which is Q1 minus 1, Q10, Q11. For L equal to 2, which is look like quadrupole, how many contributions do we have? Q2 minus 2, 2 minus 1, 2, 0, Q21, and Q22. Okay? Do we have time, about 5 minutes, or you have to run to another meeting, guys? Okay, fantastic. So let's discuss about that. So if we look at the Q00, I didn't keep the coefficient because the coefficients are given here, but look at the Q00. Q00 means that you have integral of R power of R prime power of 0, then you will have Y00 of theta prime and phi prime, rho of x prime, d3 x prime. This is exactly the monopole that we are expecting. So Y00 is equal to a constant, which can be factored out from the calculations that we had. Okay? Is 1 divided by square root of 4 pi, something like that. So this is exactly the same monopole that we do have it from Cartesian coordinate. What is happening with the Q10? What is Q10 is integral of R prime power of 1, Y10, theta prime, phi prime, rho of x prime, d3 x prime. If you do the mathematics, what you will see that is nothing more than is related to integral of z prime, rho of x prime, d3 x prime. So it looks like PZ that we have it for the Cartesian coordinate. Okay? Is a dipole moment. It looks like the dipole moment that we do have it for the Cartesian coordinate. If you do the calculation for Q11, that is a combination of PX plus I PY. If you do it for Q1 minus 1, that is look like PX minus I PY. Clear? And the expansions is really because if you look at the y11 is essentially P1 e power of I phi. And e power of I phi, you have to expand in terms of cosine and sine, and then you will get the relationship that we were looking for. It's easy. If you do the mathematics, you will get it immediately. And the same story, you can look for the Q22, Q20, Q21, and -1, and etc. And finally, you will get all relationship. The only question that is remaining for us is that here, it seems that I don't have any problem with the dipole because it seems that I have 3 components here. With these 3 components is Q11, Q10, Q1 minus 1. And the same in the Cartesian coordinate, I have Px, Py, Pz. All right. It seems that the quadrupole has a little bit of tricky part. So because here in spherical coordinates, I do have 2L plus 1 as a parameter, which means that if L is equal to 2, I have 5 independent terms, which is what we discussed, is Q22, Q2 to minus 1, Q2 0, Q2 1, and Q2 minus 2, okay? Well, if you look at the Cartesian coordinate, what we had Qij, right? And if you look at the Qij, means that I is changing from 1 to 3, J is changing from 1 to 3. So essentially, I will end up with a tensor of 3 by 3. So essentially, I have Q11, Q12, Q13, Q21, Q22, Q23, Q31, 32, 33. And of course, I know that I and J, they are symmetric. So these matrix will be symmetric. So it means that I have 1, 2, 3, 4, 5, 6 elements, independent elements, which is because Q11, 1, 2 is identical to Q21, but I have Q12, Q13, Q1, 2, 3, Q11, Q22, Q33. So how come here I have 6 independent quadrupole term, and here I have 5 independent quadrupole term? The tricky part is that here, if you look at the trace of Q matrix or tensor, the trace is equal to 0. It means that Q11 plus Q22 plus Q33 is equal to 0. So there is a relation between them which cancel out one of them to be completely independent. So one, it can be expanded in terms of the others. So again, we'll end up with 5 independent terms for the quadrupole term, which is identical to 5 independent terms that we do have it in spherical coordinates. All right? So you can do the mathematics and look at the Q11, Q22, Q23, and you will see that the trace is given by 0. So I will leave it here. I will stop here. The next lecture will be talking about materials, going inside of the materials and look at the polarization, and then looking at the dielectric terms, and maybe going even with near to 0 refractive index materials. Okay. Any questions? I will stop the video and I will see you next lecture.